Hi everyone, it's my pleasure to be with you one more time on General Practical Physics by PhET Simulation. My name is Professor Akinlolai Olayinka, and I will be glad to take you through this experiment that has been titled Verification of Planck's Constant by Photoelectric Effects. Let's quickly run along together. Now, what is the aim of this experiment that is before us? First of all, we're actually looking at examining the photoelectric effect, what it is, and then secondly, we'll be willing to also determine the value of Planck's constant experimentally. What are the specific objectives for this experiment as we go on? Number one, at the end of this exercise, the learner should be able to understand the photoelectric effect and its significance in quantum mechanics. Secondly, learners should be able to explore how light interacts with a metal target, causing the emission of electrons. Number three, learners should be able to use PhET interactive simulations to recreate photoelectric experiments. And four, learners should be able to analyze experimental data to calculate Planck's constant. Remember, Planck constant is a constant, but we should be able to verify or determine it experimentally at the end of this exercise. And lastly, learners should be able to determine the work function of known or unknown matter. Now let's look at the apparatus of interest. Like I said, we are interested in using photoelectric effect simulation provided by PhET interactive simulation located at the University of Colorado, Boulder, USA. Now, I'm glad to mention that I'm a fellow of PhET interactive simulation at a university, and I'm proud to be part of that project. Thanks to the visionary of PhET interactive simulation, that is Professor Carl Wieman, who won Nobel laureate, and in 2002, he used the fund he got for that laureate that he won to establish what is now known as PhET interactive simulation. And I need to mention that PhET interactive simulation has been used globally to change how STEM is being taught. In fact, the whole idea is STEM teaching is now just like STEM being done by the learners. Thanks to University of Colorado, thanks to all the people who are working on that project. Now, the website direct link where the photoelectric effect can be accessed is what we have here, phet.colorado.edu/en/simulations then/photoelectric. That is the page for the photoelectric simulation. Now let's go specific to downloading this particular one. Generally, you have a different type of PhET, different type of simulations on PhET interactive simulation websites. We have them in Java file, we have them in HTML5 files. So this particular one is only available in Java file. So for you to be able to run this either on your local system or even online, you need to have access to Java. Okay, so in case you download this Java file and it's not running on your system, there's no cause for alarm. All you have to do is to go to Java page and download and install the relevant Java Java requirements. Okay, now also it's possible to actually download the full package of PhET interactive simulation containing hundreds of sims. Okay, now in order to be able to do that, you can actually make use of this link I have done. The first link here is actually for the Windows app. It's about 230 something, just a little above 200 MB file. So if you download this and you install it on your Windows operating system, you have access to this simulation both in Java and several other simulations that you can make use of. And that is also available. This link is also available in this QR code, which can be scanned directly and the file can be downloaded. The second link is for users of Mac operating system, they can also download a file and install it on their Mac system, and this QR code can also give opportunity to be able to access this same file for Mac users, whereas this big QR code is for this jar file to download just photoelectric simulation for photoelectric only, not for the entire package. Okay, so let's go on now. Taking a look at this is what the simulation looks like after it has been run. Okay, so we have the light source here, you have the intensity slider here, you have the wavelength slider here. Remember, wavelength is directly related to frequency. Okay, so when we make reference to frequency or we make reference to wavelength, know that the difference between the two is just the speed of light, which is a constant. Okay, and then we have the adjuster for the voltage here, and we have a meter that is measuring the currents, that is the photo currents. Is that okay? This is what this one is being measured. Okay, and of course I've mentioned about this QR code, which can be used to access what is being done. Now I will quickly give us access to this video for us to uh, see what is being done there. So looking at the video, we can see we have to select the material of choice, and the slider I've mentioned that earlier, that is where the slider can be adjusted. Okay, then we can also see where we can adjust the wavelength as the case may be. Then we can see the electron being emitted from the sodium metal. Okay, we can also see the slider for the voltage and the photocurrent that is being measured in that place. So let's just take note of how we can interact with this when we have been able to successfully uh, run it on our system, so that we can actually make use of it effectively. Okay, so we go on. Now let's quickly run through our introduction. As a form of quick introduction, what is photoelectric effects? Photoelectric effects is actually a fascinating phenomenon, and it provides crucial evidence for the quantization of energy in quantum mechanics. In reality, the quantum theory is built around the concept of photoelectric effects. Now, when light, which can also be referred to as photons, when it strikes a metal surface, what happens there is the photon energy from the light source that has come upon the metal surface causes electron to be ejected from the metal surface, as we can see from this figure. Okay, take a look at this. This is the metal of choice in this place, for instance. Okay, and we have a light source coming here. So this light source coming to this place, what has it done? It's causing the electrons that are located in this metal to be ejected and being released. Okay, Now, the energy of this emitted electron depends solely on the frequency of the incident light rather than its intensity. So, the energy of these emitted electrons is actually a function of frequency. And as you can see earlier, when I adjusted the wavelengths, you can see that affects how those electrons are being emitted. So it's more of frequency dependent than intensity dependent. Okay. Now, this behavior cannot be explained by classical wave theory, but it aligns perfectly with the principle of quantum physics. So the idea of photoelectric effect, where you have all these concepts in discourse, perfectly aligned with quantum physics rather than classical physics theory. Now, in this experiment, we aim to explore the photoelectric effect using PhET interactive simulations. By analyzing experimental data, we will be able to determine Planck constants, which plays a fundamental role in understanding the behavior of light and matter at the atomic and subatomic level. Uh, a quick one. What are the areas of applications of this photoelectric effects? What are the area of applications? So I'll quickly just run through them. Of course, photoelectric effect finds its applications in solar cells and photovoltaics. Okay, we all, I believe majority of us are familiar with what solar cells are. Okay, solar cells are devices that convert light energy into electrical energy. And how does it done that? How is that done? Okay, the photons that are coming from the sun is being trapped by the solar cells, and that is being converted to electricity. Another application is where we have photo cells and light sensors. Of course, light sensors, we see application in so many places. For instance, you have some solar light that are located in strategic places that are not required to be on or off by anybody. Rather, they depend on sensors in order to be able to come on or go off. We have photo multiplier tubes as another aspect of applications. We have a photoelectric spectroscopy is another aspect of application of photoelectric effects. Then we have photoelectric emission microscopy. This is particularly relevant in material research and the semiconductor analysis. Okay, it's more of tools that are relevant to researchers who are looking at materials at subatomic level. The another area of application is photoelectric work function measurement, okay, which is similar to what we're trying to do here. Work function of a material is quite basic and essential to the property of that material, and then a photoelectric effect can help us to actually determine that, and definitely we're determining one even as we move on in this experiment. Okay, then photoelectric sensors in industrial automation. Okay, in robotics, in so many aspects of industrial applications, we find various photoelectric sensors playing different roles at a different time. And then we also have a photoelectric effect in chemistry. So chemists find photoelectric effect very relevant when it comes to studying chemical reactions, analysis of molecular structures, and then looking at electronic transitions in different materials. Now, we're going into the theory that is guiding the experiment we are trying to do. Okay, let's look at the theory. As mentioned earlier, the photoelectric effect is one of the key concepts that is the basis for quantum theory or quantum physics or quantum mechanics. Okay, prior to 20th century, light was considered to be a wave phenomenon. Okay, in most ways, this idea reflects reality. For example, light is bendable. Okay, so meaning it's behaving like wave. That is, a typical example is if you pass light through a lens, you can see that the light can bend. Definitely from one medium to the other, you will see that light will bend. The whole idea of that is Light, of course, of 20th century behaves like what? Behaves like wave. Okay, it has wave properties. Okay. However, Planck put this perspective in another dimension uh, by theorizing that light and other form of energy comes in packets or discrete bundles, and light in his theory was then considered or is then considered as particle, which are now called or referred to as photon. Okay, so the idea is this: rather than considering light as just a wave, light is now being considered also as a particle. Of course, definitely the explanation of the particle behavior of light is not within the concept of a classical physics, but rather quantum physics as a robust explanation to that. And you can see from the figure we have at the right side here, okay, you can see light. These are photons of light coming upon this metal surface. You can see the electron that are arranged in this metal. Okay, so what happened to them? Because of this light wave striking this material, okay, definitely what is happening, then they are being emitted out of this surface. Okay, they are being emitted out of this surface. Now let's continue. The photoelectric effect was explained by Einstein when he conjectured that Planck's bundles of energy, that is photons, were knocking loose the electrons, but they can only knock loose the electrons if the photon has enough energy to do the job. It's just like this. For a 2-year-old boy to be able to knock down a football player might be an impossible task. Okay? Because of course a 2-year-old boy might not even be able to do anything, to even move, to even push an talk less of knocking him off his feet. Okay, but when you ask maybe somebody who is a bull to now come and knock down a football player, definitely you can believe, you will agree with me that that is possible. Okay, so before photons will be able to knock out electrons from any metal surface, definitely it must have enough energy to be able to do the job. Okay, now Planck's hypothesis states that light in a black body radiation experiment coexist only in discrete bundles with energy which is given as E is equal to hv. Now the v in that place is not velocity. Please take note of it. In some other text you might see it written as hf. That v is actually frequency of the incident light. Please take note of this. This v is frequency of the incident light, where this h is your Planck constant, okay, and E is the energy, okay, giving us this. And then this our V, which is the frequency, can then be written as what? C over lambda. C over lambda, where C is also another constant, which is the speed of light, and lambda is the wavelength. As you saw earlier from the slider, you can see the wavelength in nanometer being written in that simulation. So if you need frequency, all you have to do is to come and bring in this formula. V is equal to what? C over lambda, where your V will then become your what? Become your frequency that you might need for calculation or for any other activity. Okay, now different metals hold on to their electrons more strongly or weakly due to the atomic structures, and the work function, which is also written as phi, for different metals varies. That is, different metals, different materials have different wave function, and this different work function, not wave function, please. Okay, different work function, and this work function for different metals varies. For instance, aluminium has a work function of 4.08 electron volts, while cesium has work function of 2.1 electron volts. Coming down here, we have sodium 2.28 electron volts. Platinum, on the other hand, has a very high a very high work function of the value of 6.35 electron volts. So the implication of all this is that different metals have different work function. Now, the kinetic energy of the electron refers to its actual movement once ejected, and this is represented as E subscript K. It can effectively be ignored if we just reach the amount of energy to lose the electron but not get it moving. Ek in this circumstance will essentially have a value of 0. The idea is this: if you get enough energy to knock the electron off the metal, but the electron is just knocked off, it's not moving, okay, no kinetic energy, the kinetic energy in that situation will become 0, okay. But that energy that knock it off, that is the work function of that particular material. Okay, let's look at some mathematics. Okay, the work function is related with this equation. Remember, this HV is also referred to as what? E, the Planck energy. Okay, E is equal to HV. Okay, and it can be written as what? EK plus phi, that is the kinetic energy plus the work function. Okay, I've defined all this one earlier. So our Planck constant has a value of 6.626 times 10 raised to minus 34 joule seconds, and is the same thing as 4.14 times 10 raised to minus 15 electron volt seconds. Okay, V is the frequency of the incident light, and E subscript K is the kinetic energy of the ejected electron. Now, if photon has enough energy, electron emerges with the kinetic energy Ke, which is equal to the photon energy minus the work function. Remember, we said earlier, if the kinetic energy is 0, it means the electrons are just broken loose from the metal surface, but they are not moving. At that point in time, what we will have is that this one will become 0, so HV will be equal to phi. Okay, but in a situation whereby they are moving, then we will have our kinetic energy to be equal to HV minus phi. Okay, and then we can also write our phi, which is the work function, as HV subscript HV naught. Okay, where your V naught is talking about what? The initial velocity. Okay, now, sorry, initial frequency, please. Okay, now let's go through the procedure that we need to follow to be able to achieve this experiment. Now, the first thing to be done is to select the metal of choice. In the first part of this procedure, we are to select platinum, so you can click here and select platinum. Okay, then next, set light intensity to 100%, which is just to move the slider to 100%. Then vary wavelengths from 100 nanometer to 160 nanometer. Okay, so the value of this wavelength can simply be typed here. Just click on this, type 100 and press enter on the keyboard. So we have this, and once it is done, record the currents in each case. After it is done, you can go to 110, 120, 130, and so on and so forth to get 160 and record the currents in each case. Okay, and the table will look like this. This is for 100, you have the value for current, 110 up to the last one. Now, this table says tabulate your reading using this table as a guide. Note that E is equal to HV is equal to C over lambda. Now, this frequency V in Hertz will be calculated from this value. In this case, we have 100 nanometer. 100 nanometer is the same thing as 100 times 10 raised to power minus 9 meter. Nano is times 10 raised to power minus 9. So take note of that. And so if you are looking for V, meaning we will have V is equal to C over lambda, and C the speed of light, and then divided by what? By lambda in this case. Okay, and that will give us the frequency, and that will also be done. Once that is done, then we can use this formula E is equal to HV to calculate this, and this table will be completed. Once the table is completed, these are the questions to be attempted under this procedure 1. After the table is completed, number 2, plot the graph. Number 1, complete the table above and plot the graph of E in electron volts against frequency V. Okay, now there is a specification of the units to be used, electron volts. So let me quickly go back. In order to be able to achieve that, it's not a difficult thing. In order to be able to achieve that, earlier you were given a Planck constants in both Joule seconds and electron volt seconds. So if you are calculating your E and you want the unit to be in electron volts, all you have to do is to simply use a Planck constant that is expressed in electron volts seconds, and whatever you have calculated will be in electron volts. Okay, and so from your graph, deduce the Planck constant. So having plotted the graph of E against V, meaning the slope will be the Planck constant. This question says from your graph deduce the Planck constant. So we're simply saying calculate the what? The slope of your graph. Okay, then having done that, taking average of the data in the table above, determine the initial kinetic energy of the electron as it comes out of matter. Determine the initial kinetic energy of the electron as it comes out of the matter. Take the platinum work function to be 6.35. So that is also just applying the formula, and then you can calculate that. And the last question here says, list 2 precautions in carrying out this experiment in physical laboratory environment. Next, here we are looking at the procedure number 2. Under this procedure, we are to choose the unknown matter. Of course, the unknown matter is represented with question here. Okay, so once that is chosen, set the intensity as usual earlier to 100. That is also done here. Okay, then vary wavelength of the incident light. Keep it monochromatic. Okay, just let the light be monochromatic, not any of these colored lights. Okay, let it be monochrome. Okay, and then using the slider, note the wavelengths and use it to obtain the frequency. Okay, this slider, after you have put it in any of these monochromatic zone, okay, then you can go ahead and read the value of this wavelength here. I haven't gotten the value of this wavelength, use it to calculate the frequency and keep it aside. Okay, then next, observe the emission of photoelectrons and photoelectric current. Of course, the meter will show, we will see the electron being emitted and moving, and we also see that a photoelectric current is actually flowing through the circuits. Okay, after that, then to measure the stopping voltage, we need the stopping voltage in order for us to be able to calculate the work function. So to measure what is known as the stopping voltage, connect the unknown meter to the negative terminal of the battery. Okay, the battery down has positive and negative terminal. Okay, how do you achieve that? Gradually increase the voltage in reverse potential. Be reversing the battery backward, and you will see that the polarity will shift. Okay, until the photo current stops flowing completely and drops to 0. So as you're adjusting, you will notice that the current on the ammeter in the circuit will keep dropping, and once it gets to 0, then you then take the value of that voltage on that battery. Usually it might be a negative voltage. Okay, so take the value of that voltage. Once you take the value of that voltage, that is your stopping voltage. Haven't gotten your stopping voltage, then you need to pay attention to this in order to be able to calculate the work function. Okay, work function is related to stopping voltage as phi is equal to EV, where this V is talking about the voltage, the stopping voltage, and E is the electronic charge, 1.6 times 10 to the power minus 19 coulomb. And then you have HV, you are familiar with this, and every other thing you are familiar with. Okay. Now, EK is the kinetic energy of the emitted electron. And because at that point in time, there is no movement of electrons, okay, meaning EK will also become 0. Then we can have our phi to be equal to what? HV minus EV, okay? So HV minus EV, that is what we will have. And having gotten this, then we can then go ahead and identify the matter by comparing the calculated work function with the values we have in the table shown earlier. And then we can then identify the unknown matter based on the closest match to the known work function. Okay, the value gotten from here can then be compared and then be matched to the closest value in the work function table. And I think that is the end. I will leave you with this quote. In the dance of light and matter, the photoelectric effect whispers the secret of quantum reality. A reminder that even the tiniest particle holds profound mystery. Keep exploring, keep learning, and keep winning. God bless you. Thank you for listening.